Hello everyone. We are starting a free open lecture in our Discord. All our lectures are held weekly without breaks. If you, the viewer, want to ask questions online and get answers, join our lectures. You can find the link to Discord in our Telegram channel. To find out the schedule of the lectures, join our Telegram channel. Well, today we will discuss in depth about CPU-bound load. Last time, it was about input-output load, and the main problem we faced there was the waiting time. When our processor was simply idle, absolutely doing nothing, literally just waiting for a response. And this problem was essentially solved by using the processor while one of the tasks, that is, some request, is inherently idle and waiting. Now, in a sense, we will basically consider the opposite situation. Fundamentally, when our CPU resources or some other computing device, it could be a graphics card, for example, various GPUs, are busy and you could say are not idle at all. And we actually lack them, on the contrary. And what tasks typically solved here when there is a CPU-bound load? This is some kind of processing. For example, we have a service that processes photos, videos, or audio in some way, or a neural network is considered like a GPT chat. Accordingly, there are a lot of multiplications. There is a significant load on the computational device. In general, most tasks from competitive programming are indeed CPU-bound. The task is to calculate something as quickly as possible, efficiently and effectively, without any unnecessary delay or hesitation. And during these calculations, the processor is indeed loaded. It's simple. How the request goes. The request comes to us and it loads the processor. It is processed for a certain amount of time, let's say 1 second as well, and during all this time the processor is loaded. It doesn't wait for anyone, it works. This is only for one request. Accordingly,
Want to become a great programmer? Subscribe to our Telegram channel.
what will happen here in this scenario? Precisely the exact same situation that occurred. The I/O-bound load will happen. If we, for example, send 3 requests simultaneously, then the first request will be processed in 1 second. This is its normal processing time. The second request will wait until the first one is executed, and only after the first one is executed, it will start executing itself here. And the third request, it will be wait for both the first and second, and it will only start executing to the second. Accordingly, the waiting time for each subsequent request will also grow linearly, just as it was in I/O bound. Well, let's immediately move on to a specific example that we will optimize further. We also have some API here and one request. What does this request do? We currently have a task that finds the sum of natural numbers from 1 to n, finds it in a loop for now in order to calculate. Well, accordingly, if we pass a relatively large number here, approximately around 10 to the 7th or so, this little 5 will be quite enough. It will get stuck. That is, the sum from 1 to 10 to the 7th will take about a second to calculate. Well, accordingly, if we pass an even larger number, like 10 to the 9th, it will take significantly longer, around 100 seconds, maybe even a bit more than 100 seconds. Well, accordingly, if we pass anything else, the times will be astronomical, and we won't consider that for now, because, well, accordingly, if we set a limit for some 10 to the 9th number, we will need to adjust the algorithm itself somehow, because even if we apply, we will look at parallel computations later. They won't help much here either. Well, that means our simple application that calculates the sum of numbers in a loop from 1 to n. Again, we have code for sending requests here, so we pass a number of about 1.7 times 10 to the 7th, so that it calculates for about a second and picks such a number. And what we get is that when we sent 5 requests in parallel, the first request took 1 second, the second 2 seconds, the third 3, the fourth 4, and the fifth 5. So with parallel sending, the waiting time for each subsequent request grows linearly, increasing by 1 second. And we want to optimize this somehow, which means what we want to achieve. Well, in an ideal scenario, in an ideal world, we want all of the requests to respond in the same time, and that time should be within 1 second, or for the time to be significantly reduced. Here, for example, we can leave some linear option, meaning the time will still be extended, but the request processing will not take 1 second, but rather 1/100th of a second. In fact, that would already be very positive indeed. Now let us discuss in detail what exactly we have applied in the various previous instances. That is, for I/O-bound loads, we used asynchronicity to optimize waits, or concurrency. What will happen if we apply asynchronicity? Well, in fact, asynchronicity will not do anything here. It will only worsen the situation, because we use asynchronicity only where there are waits. It will not work anywhere else. Well, accordingly, since there is no idle time, I definitely won't do anything better synchronously here. So let's move on to concurrency. It works quite interestingly. I remind you, concurrency allows us to do what? I have 2 tasks, and it allows switching between them within a single CPU core. First the red one was executed, then the green one, then again red, then green. And so it was executed in parts. The waiting was overall. As a result, we ultimately optimized in I/O bounty, but we optimized here at the point that the waits here and there coincided, and it turned out that we were waiting for 2 tasks in parallel in the process. And if we look at the parts that are executed, that is the red-green alternation, and here too the red-green alternation, the CPU is occupied here. It is important to understand that the first half of the color red combined with the first half of the color green did not consume as much CPU processing time as just one of these colors on its own. Accordingly, if the CPU is busy, then concurrency will not be utilized very well here. And where is it exactly here? Here, right at concurrency. Let's definitely try to use it. Take async here so that UVcorn enables it by itself. Then each function will run in a separate thread, TFSP. And what will happen? Each request started to execute in about 5 seconds. What did concurrency do? It did not reduce the request time, but it equalized the request time for each one. Moreover, it equalized not. Not every request is processed in 1 second, but to a greater extent. That is, if we receive 5 requests, then with a regular implementation, the last request will be completed in 5 seconds, and the response will come. So here, essentially, the responses to all requests will come only when the 5th one is completely processed. Therefore, overall, concurrency only made things worse here. Only the 5th was waiting. Here, everyone is waiting for the 5th. So, concurrency here too. Unfortunately, it won't work very well, as you might expect in the current situation, as there are no downtimes. Well, and... no, not well. Let's see. Do you have any questions? If not, then let's move on to discuss how to optimize all of this effectively. The main approaches to optimizing CPU-bound tasks with calculations and the processor occupied are either using parallel computing, we add additional CPU cores, or even entire computers to perform this task. And then we can actually execute several requests simultaneously in parallel. Or the second option is that we try to optimize the algorithm efficiently. That is, we will still do everything the same way, but significantly reduce the complexity of the algorithm, and accordingly the time it takes for this algorithm to execute, so that our request will not take 1 second, but for example 1/100th of a second. And then in just 1 second we will execute not one request but 100. This will provide a very significant and noticeable boost to overall system performance and efficiency. The scheme remains essentially the same compared to what was here at the beginning. Absolutely the same, only the beginning the request was processed in 1 second, and if we optimize the algorithm somehow, it will take, for example, 1 second. Here is a fairly simple task. We calculate the sum of numbers from 1 to n, and this wonderful formula is also covered in middle school, which essentially allows us to rapidly calculate the sum of literal numbers from 1 to n. So basically, this is the sum of an arithmetic progression for us. And accordingly, if we had a loop, and we need to iterate through all the numbers, and we have n numbers, then the computational complexity of the loop is n. Here, we only have the formula, which executes in constant time, so the complexity here will be 1. And if we simply rewrite this task, where we previously had a loop, and now we just have the formula, we will get the average response time for the request. It's not 1/100th of a second, of course, but within that range. As we can see, the response time for the request also grows linearly because it was 0.2, then became 0.3, 0.4, 0.6, 0.8. That is, approximately each request is processed in about 0.02 seconds. But this is indeed quite acceptable because we can process 100 requests per second. This is indeed already considerably better, significantly better than before, in comparison to the past, when our request took a whole second. What can we try to do? We can try to somehow equalize the request times using parallel computing. This option for optimizing the algorithm itself is, in fact, indeed very efficient and extremely effective in many ways. It is great. If such a solution exists, it will generally be several times more effective than parallel computing, especially if we can, in a manner that is both significantly and effectively, diminish the overall complexity, like down to a constant beyond the line. And if there are still perhaps something like geometric shapes such as squares, cubes, then it will be even more noticeable. This method is not always applicable. Firstly, it is complex, meaning you really need to think about how to optimize the algorithm to reduce complexity. Secondly, it can be costly and financially demanding for businesses because you need to find someone who can handle it appropriately, and resources. And overall, in general, it seems that the task may not be very feasible within a reasonable time frame, as quite a significant amount of time and effort might be required, because the algorithm is already the best known at this point in time, furthermore, and from there you simply just need to invent further. Well, there are some tasks that simply cannot be solved any faster, because they have certain specific mathematical limitations in their capabilities, and this is all proven. Accordingly, the method is indeed excellent for reducing computational complexity, but it will not always work. Now we will consider, in a very detailed and comprehensive manner, the methods that can be used almost always. Well, one can certainly indeed be used all the time. The second one is used a bit less often, but still quite frequently. Then always, but still much more often than algorithmic optimization. So, in general, the use of parallel computing. What are we doing? Well, first of all, this method will definitely work on modern multi-core processors. If we have a single core in the processor, then it simply cannot work physically in any modern computing environment, or we will need another computer to compute additional processing tasks in parallel, along with the one where our application is running, or a multi-core processor, so that a task can be selected in parallel on one computer. So, what is its purpose? Here we have a total of 3 requests, and the processing of each request is assigned to one of the 3 cores in the system. That's all, in total. Here we can now process not just 1 request per second as before, but in fact 3 or even more as a result. At the same time, the execution time of the request remains exactly 1 second. But what is important to understand here? It is important to understand that if requests come in parallel.
Want to become a great programmer? Subscribe to our Telegram channel.